Hi everyone, let's start with a little warm-up going over 21.2 and 21.3 permutations and combinations. So we're just going to decide whether the following situations are a permutation or a combination. So we're going to think about whether or not order matters. So remember, order does matter for permutations and it does not matter for combinations. So for number one, a team of 8 basketball players needs to choose a captain and a co-captain. So order matters here because it matters which person is the captain and which person is the co-captain. So this is going to be a permutation. And the way that we'd calculate this permutation is we have 8 people and we're picking 2 of them. Okay, so 8 pick 2. All right, Anthony and Aiden are planning trips to 9 countries this year. There are 13 countries they would like to visit. They are deciding which countries to skip. So here, order does not matter. They're just deciding which countries to go to. They're not deciding the order in which to go to those countries. So this one would be a combination. And the way we pick that is they're planning trips to 9 and we have 13 to choose from. So 13 choose 9 is how we calculate how many countries out of 13 they will visit. Okay, the batting order for 7 players on a 12-person team. Obviously, this one matters. There's even the word order in there, so order does matter here, so that would make this a permutation. And we would do 12, and we're picking 7 of them for their batting order. And then the last one, I'm going to move the video out of the way so you can see it. There are 45 applicants for 3 computer programmer positions. Again, order doesn't matter. We're just picking 3 to be computer programmers. So this one is a combination because of the fact order doesn't matter. And the way we'd calculate this is we have 45 people and we are choosing 3 of them for those positions. All right, this is the last section of module 21. It's 21.4. We're going to talk about mutually exclusive events and overlapping events. So we'll identify whether or not an event is mutually exclusive, and then we'll calculate probabilities involving both mutually exclusive and overlapping events. So we'll start with mutually exclusive. 2 events are mutually exclusive if they cannot both occur in the same trial of an experiment. So for example, heads and tails. If you're flipping a coin, can you get both heads and tails at the same time? No, you can't. So those 2 events would be considered mutually exclusive. There's no overlap between them. Okay. So the formula we use, though this is the probability that either A or B occurs, that's going to be equal to the probability of A plus the probability of B. Now remember, we can only use this formula if our events are defined as mutually exclusive. So let's do an example. Let A be the event that you roll an even number, and let B be the event that you roll a 5. So first we're going to draw a Venn diagram, just kind of displaying the fact that these 2 events are mutually exclusive. There's no overlap. So this box is going to represent my sample space. Inside of it is going to be all the possibilities we have when we roll a die. So I'm going to draw a circle for event A. I'm going to draw a separate circle for event B. My circles don't touch because they're mutually exclusive. There's no overlap between them. There's no outcomes in common between event A and event B. So some events in A is rolling an even number. So if we roll a 2, if we roll a 4, if we roll a 6, those are all outcomes that would be considered event A, since those are all even numbers. Event B is just rolling a 5, so that's the only outcome we have in event B. And then events that are in neither event A or event B would be rolling a 1 or rolling a 6, because those are, oh, sorry, I don't know why I wrote a 6 there. I meant to write a 3. I was like, 6 is even. So the outcomes that are neither in event A or event B are 1 and 3, because those are odd and they're not 5. So they're in neither of those 2 events. So now let's go ahead and calculate the probability of A or B. So we're going to go ahead and we're going to use the formula from up there, probability of A plus the probability of B. Well, we know we have 6 outcomes total when we roll a die, so the probability of event A would be 3 out of 6. And then the probability of event B would be 1 out of 6. So that would be a total of 4 out of 6, or if we simplify, 2/3. So there's a 2/3 chance that we either roll an even number or we roll a 5. All right, so now let's talk about overlapping events. 2 events are overlapping. We can also call them inclusive events if they have one or more outcomes in common. So if you were to display them in a Venn diagram, there would be overlap between your 2 circles. And the formula we use for overlapping events, probability of A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. So let A be the event that you roll an even number and B be the event that you roll a 3 or greater. So let's draw a Venn diagram for this sample space and then we'll calculate the probability of event A or B. So again, this box represents my sample space. Inside, we're going to put all possible outcomes we have when we roll a die. And this time when I draw my 2 circles, well, I'm going to attempt for there to be some overlap between them. So this circle is going to be event A. This circle is going to be event B. So let's go ahead and classify some stuff. First, let's put in all the things they have in common, the overlap. So A is rolling an even number. B is rolling a 3 or greater. So things that are numbers that are both even and 3 or greater are going to go in the middle here. So that would be 4 and 6. Those numbers satisfy both event A and event B. Okay, event A is just even, so the only other thing we have is 2. And then B is rolling a 3 or greater, so 3 and 5. And then outside of those 2 events is just one outcome, it's rolling a 1. 1 is neither even nor is it 3 or greater, so it's going to go outside of those 2 events. So now we can go ahead and use the formula above to calculate the probability of A or B. Okay, probability of A, everything inside of A, we have 3 outcomes, so 3 out of 6. Okay. Plus probability of B, so in event B, we have 4 out of 6 outcomes. And then we're going to subtract out the intersection A and B. So inside of both circles is 2 events, so we'll subtract out 2 out of 6. So that gives us 5 out of 6. There's a 5/6 chance we'll roll either an even number or we'll roll a 3 or greater. The last example we're going to do is with a 2-way table. This is just a way to classify some data we collect. So we have freshman, sophomore, junior, senior, and then we have boy or girl, and we have a total of 808 people. So let's use this table to find some probabilities. So what's the probability that we pick a senior? So we can just use the totals for that. We have 202 seniors out of 808 people total. So the probability that we pick a senior is 1/4. All right, senior and girl. So this is the intersection. They have to be both a senior and a girl. So if we look at the table, that's this number right here. We have 108 seniors that are also girls out of 808 people total. And that gives us about 13.4%. Okay, last one is probability of senior or a girl. So these events are overlapping because someone can be a senior and a girl at the same time. So we're going to use the overlapping formula. Probability of senior plus the probability of a girl minus the probability of senior and girl. So we already calculated probability of a senior. That was 202 out of 808. Okay, girl, we have 412 girls out of 808 people total. And then we'll subtract out the intersection, which we found in number 2, 108 senior girls out of 808 people total. So that gives us 506 out of 808. And then if we simplify that, we get approximately 63%. So there's a 63% chance we choose either a senior or a girl. So that was the last example, a little bit shorter of a lesson than last time. So again, email me if you guys have any questions or come visit virtual office hours. Thanks, guys.